already plugged in. Not yet. It's coming. Yes, coming. Yes. So this lecture will be continuing from the previous one, but give you or present you a different example of the thermomechanical modeling of additive manufacturing. I would say it's more like a fusion-based melting process. So in this case, as you may know, some of the experiment has been done in the single bead kind of experiment. So we try to mimic that to our simulation. So you can think as a welding cases or whatsoever, because people may do single bead with powder or without powder. But the point here is not about that boundary condition only, but it's about how we actually translate the information from experiment and then validate the model to predict correctly the residual phase development. So this is based on one of my active paper in the fusion welding simulation. So this is in this slide you will see I would say power of lasers actually lower and higher, and then this will change completely from the conduction mode to the keyhole mode, for example, and that actually changed the microstructure as well from equax to columnar grains. And as you may see here from a kind of snapshot, this picture may summarize already what happened here, and then what the consequence of this microstructure to property. This is what we are going to talk. And finally, we want to know this area, as I said before, this may lead to failure, like you see crack here initiate in this zone. So the presentation of this lecture actually comprise of some introduction and motivation. What is the aim and methodology that we're going to use for this lecture? And then again, you will see a lot of word of ICME or integrated computational material engineering framework that we apply for this fusion-based manufacturing process or fusion additive manufacturing. In this case, they are powder-based fusion anyway. And then in the term of computational fluid dynamics calculation, we want to capture 5 things here. The first one, the keyhole formation validated with high-speed imaging. Keyhole instability, steady state whirlpool geometry. All of this has been validated with some form of experiment. Fluid dynamics in the whirlpool, porosity formation with available experimental information, whirlpool geometry, and also temperature history. So this is what we call processing induced defect, because induced by the process. And then this next one is a microstructure. As I said before, we cannot talk separately from process, microstructure, and property. Things has to come in one go, in one package. So in microstructure, we're talking about well solidification microstructure, the linkage of the CFD to cellular automata and finite element calculation. Either actually is a partial penetration or conduction mode or full penetration or keyhole mode that you use in industry. And then how can we actually talking this, apply this framework? Again, now it is important for the not mechanical engineer. You also need to understand about what is the material system you are looking at. This may change from system to system. If you talk about steel, you have duplex steel, or you have just like ferritic steel. It's so different framework as well from mechanical perspective, right? It's the same. So the model alloy we used here is a 2-phase titanium alloy, which is gamma beta system. And then the linkage between cellular automata, microstructure, and the crystal plasticity. And how can we talk about the static property yield stress here? Again, the simplest, but it's complicated enough, believe me, to link this location-specific prediction. As you've seen in the previous lecture, that at different locations you may get different structure and hence different property anticipated. So just to remind you, I mean, this is the same as yesterday. So we are talking about fusion-based process. This may be applied to welding, additive manufacturing, and also if you don't want to, or you want to approximate the electron beam melting as well, this may be able to apply, or electron beam additive manufacturing. So the introduction of this is actually fusion welding or fusion melting, I would say, is a joining process, is a joining of material process, and across the various industry applications, including aerospace. I think I don't need to actually emphasize about how important of the fusion-based manufacturing process to you. But to obtain the weld integrity, or I would say the structural integrity, which means defect-free weld, we need to determine the location-specific property. And the approach we are going to use is integrated computational engineering approach. I kind of actually give you the result before actually I'm talking to you, but this is what we've seen from experiment when we vary the power, laser power, for example, in this case, and then it changed the mode from conduction to keyhole mode. And this mechanical property as a function of microstructure is required for component design and process improvement. I think that's what I'm also emphasizing a lot in the past. And in this work, in this presentation, in this beginning of this section, we will talk about titanium 6-4. So it's required that you may see this is the experiment, again, inspiration from experiment. If you use the different scanning speed, for example, and then you control the laser power, you can actually change your welded microstructure or fusion melted microstructure here from columnar grains to E-cracks easily. If you use very slow melting or slow scan speed, this actually will come E-cracks. But if it's fast scan speed, it's just about 4 times faster, you will get E-crack structure. And this E-crack structure may be quite detrimental to the part or to the component that you are going to build. Like this, you will see this is the sensitive area. And then probably some of the simulation I'm going to show you now can tell you a little bit more why. So this is the design for process. As I said, we need to understand what is the strain rate and the scale that we are looking at. So we are talking about quite low strain rate in this case, and also quite micro scale here. So this is the simulation that you've seen yesterday that I'm talking that we can simulate anything on Earth actually under assumption made. You will see here from the superplastic forming, spin forming, ring rotary friction welding, linear friction welding, and then machining here. I mean, it's all intensive and a lot of calculation and also solid mechanics needed. I think from mechanical engineering people, I think you know how complicated it is. And how can we actually now, all these are solid state forming, or this one is thermomechanical process. This is also thermomechanical process. But there's nothing related to melting. What we are going to do next is to motivate from that inspiration here to do some melting process. So what does an engineer wish to be able to predict on a well? I mean, on a well or AM, I mean, that's something we apply to AM later. So in order to do the thermal liquid flow here, we use fluid dynamics or computational fluid dynamics to understand the well crown trough formation, which is crown mean crown here, toes mean this one, right? Formation mechanism. Understand the keyhole phase formation. What is the vapor phase in the molten pool here at a high energy density well or AM. Predict the bead and the melt pool shape, and this is what we get from melt pool. More than that, we will get the thermal history, we get the surface roughness, we get the porosity as well. Again, this is something I haven't mentioned here yet. But in terms of the stress distortion, we want to predict a true process field. And then this used for solid mechanics. So as mechanical engineer, it may relevant to you more now. Understand the tooling or cramping constraint as well, if it's applied to your system. And this well structure on integrity, that's actually related to the detail that you used before on the prediction of porosity and defect and well-zoned microstructure in terms of grain size. Again, we cannot decouple all this from the mechanical simulation. We have to take everything together, right? Grain size, grain orientation, well-zoned microstructure, and then crystal plasticity modeling. In the welded zone material property. Again, this is the simulation from this condition unwell investigated. You can see some particle. This is not particle. This is a porosity which is induced during the process that's trapped inside the well. And this is a 1 millimeter thickness, I think. And this is what happened. This CFD framework we use to simulate the shape and the physical phenomenon of the whirlpool, and this has been developed. And this, to actually, we need to combine this in the multi-scale modeling activity to predict the component behavior. So based on the thermophysical property and physical description of titanium 6 for material property, we can actually gain insight into the material behavior, especially the property. Like this. This is the whirlpool dynamics. This is a whirlpool envelope here with the crown and the toe, and try to predict the microstructure, what happened. Extract some microstructure, represent this well meant, and then you predict some property. That is the talk for the first part of this lecture. And then multi-scale, this is a multi-scale problem, as you see. And then CFD can successfully predict the keyhole. Validate with the thermal camera. I will show you a bit later, which you've seen something yesterday already as well. And then we link this Serratomata to the grain growth prediction, and link this CA to crystal plasticity model to predict the material property distribution across the whirlpool. And this component level property prediction is based on the homogenization. I think this is a term that you may be familiar more than me. This is homogenization and of full field solution in the multi-scale modeling framework here. So in order to develop this modeling approach, I want to be a bit more specific now, not too generic like in the previous 3 lectures. So for this particular probably single beat problem, we need to analyze the micrograph of the cross section, because we want to actually calibrate our model as well. So the whirlpool model has to be calibrated against the experimentation. So we will use multi-scale, multi-physics approach to use CFD to predict the whirlpool, and then link this to Serratomata for the grain growth, and then link this again to crystal plasticity for the material property prediction. All link potentially to get a stable finite element model for the component analysis. That is the aim and objective. And then in order to do this CFD, we need to include the real physical phenomenon. I didn't actually mention explicitly in the previous talk, but it's actually now. It's probably good time that we have the multi-phase material with solid, liquid, vapor phases. That means it's going to be, but in this case, in the simulation I'm showing you now, about to show you now, is just 2-phase problem. But 2-phase means the metal phase and then gaseous phase. We will talk you later. And conservation of momentum and energy. We have absorptivity term. We're looking at the effect of surface tension, Marangoni force, Draghi term to damp the velocity at the solid, so liquid-solid interface term, vapor pressure, reaction force, and then we have evaporation. It's all this physical phenomenon has been taken into account, and we believe this is sufficient to actually capture what happened during the process. And this is what a schematic diagram showing across length scale, that this is what we do and what we want to achieve using different computational tools. Again, that's what I want to emphasize. Things have to be integrated. It's not just individual things can happen. And this actually from the whirlpool physics-based simulation using open form, you can use, this is in micro scale, a keyhole formation, melt dynamics, porosity formation, whirlpool geometry, and temperature history here. So this is a kind of flow pattern. You will see what happened in this flow, and then the flow pattern in maximum velocity is quite reasonable, about 3 meters a second. And then this is the predicted temperature field. This is a heat affected zone, something like that. And then you'll see it's quite good agreement with experimental work validate here. And this, after that, we have the reconstruction of the melt pool. The linkage is so important. We link the liquid, this temperature contour of at the surface, liquid at surface here, and volume of this melt pool. We extract the temperature field of this one, map this one, mapping the cooling rate at the boundary here, because everything inside is basically liquid. So we want to simulate solidification for this problem. So in the next simulation phase, we use Xera Automata finite element calculation. I mean, this is an early stage. You may know the commercial software packages called Procast. It's by ESI Group. Quite expensive as well, but this is one of the EU Rolls-Royce project that I'm working long time ago. So just show you an example. So we want to simulate well microstructures, approximately the solidification, but not detailed like I show you previous lecture. And then the grain nucleation, growth and morphology and texture here. And after that, we link this microstructure reconstruction again using the, at the moment, that time, I think it's about 2014-15, we use Dream 3D, which is more robust Dream 3D now for the 3D microstructure reconstruction. Again, if you do a lot of EBSD serial measurement, you may use Dream 3D to reconstruct your microstructure for finite element calculation as well. So we use Dream 3D and PPM to write the Abacus input file, because we need to link the software as well. So we need to do some coding, programming to define the boundary. It's not one single button to place this and everything come out on one go. No. At that early stage of development, we need to do this. And then we apply the mechanical boundary condition, which is actually derived from the melt pool calculation onto the boundary here. And then next step, we use Abacus STD, I mean, in the user-defined subroutine to actually simulate the two-phase titanium constitutive law using some dislocation density-based crystal plasticity code to predict the location-specific property, such as the static property use stress here. And this is one of the example of the result. The solid dot represent the experimental result from the alpha-beta phase here, and then you see the model in the open circle here is experimental, and solid line is modeling. This is a macro scale, and then that's what we are going to talk and focus more on this part for this lecture. So again, the key of this is the integration. I think you may appreciate that what I showed you previously is increasing the length scale. So you basically scale up to larger length scale from meso or micro to macro scale. So the baseline of this computational fluid dynamics with other length scale, we need to consider what is a true physical phenomenon that require for integration. That is important. I mean, still this is a challenge in the computational material engineering community to link information from each length scale. And this probably very first of its kind that show, I mean, because the work has been published in 2016, 17, so it's probably very first paper that we show this. And then the link of the Xera Automata to the location-specific grain prediction is important. Link of this microstructure to this location crystal plasticity-based model, but this is for titanium 6-4. It will predict the material property. And link this FE to component behavior. Again, is another matter. So integration is remain one of the more challenging aspects of the computational material engineering community. First is about Frostian microstructure prediction. This is I would say, initial condition for what we're going to do. So basically, just recap, this is the mathematical framework we use. Simple than the first slide, first lecture, which we will talk more in day 4, day 5, I think that one. So we will include the physics that just repeat again the multi-phase material, solid, liquid, vapor, right? Conservation of momentum, conservation energy, absorptivity, surface tension, Marangoni force, Draghi terms, solid, liquid interface here, vapor pressure, reaction force, and evaporation. So we didn't show some other phases which is present here, but we focus more on the whirlpool dynamics here, what happened. And then you will see it's collapsing, and then it's, you see there is some instant that everything actually collapse and come back again. So this may be better represent here, so you will see what happened. You watch carefully. This one will be, you see this part is collapsing and then coming back, and this oscillating all the time, and which is quite interesting. And I can say that after we publish the work, a lot of work coming out, and then you may see more and more in additive manufacturing that they can predict the dynamics of this very well, probably a lot better than us, the first approximation here. But anyway, we capture all the surface deformation, materials recirculation, so this may cause to this street of the porosity, which is trapped inside the fusion speed zone, and then they will have defect formation here. So if we take a snapshot at a different time scale, and then we try to look at this problem as a function of radius of the laser beam. Again, what we can change is just the beam radius. We cannot change the shape at that time of the experimental facility that we have. We change the beam radius from 200, 300, and 400. And this is because this is for aerospace application. They want a very clean, well-joined region at that time. So they change, and this is the dynamics of the melt pool, if you see. So if you use smaller beam size, you will get a very narrow, shallow, melt pool. And then the map of this is actually on the keyhole surface, so we call liquid vapor surface here. And you will see that the temperature doesn't actually, not actually homogeneous. There's some absorptivity effect present here. You see some zone is yellow and red. That means some, due to the term we impose here. And then when you increase the beam radius, the melt pool become larger and larger. So we try to compare. And then you see the keyhole are formed due to the laser heat source here, heat up at specific location until vaporization occur and create vapor pressure, pushing away the metallic gaseous interface down to the plate. So it's drilling down to the plate. It's actually happen as well in additive, but the difference of additive and this, actually you have powder particle which actually increase the surface area in your domain, and then this may change your absorption a little bit. And leaving behind some narrow, hollow hole give rise to smooth joining part. Again, this is application of this is basically want to join something at the end. But this is something you've seen previously. We use high-speed imaging of, at that time, is about only 10,000 frames per second. I think I heard that there are the maximum I heard is probably 100K frames per second, but I may be wrong, but I think this is the case now. So that means a huge amount of data generated. And this is the work carried out in about, I think about 11 years ago. So things may change a lot, I believe, since then. And then capture the keyhole formation at the edge of the material. And then you will see that the modeling and the experiment show a good agreement with each other. And then what is the keyhole instability? If we investigate a little bit more about the keyhole here, you will see if I take a snapshot, there will be some incident that, every 10 millisecond. I would say 10 millisecond for additive is too long. We're talking by microsecond in additive. So just want to show you the kinetic of keyhole can physically captured. Even we can say something we call fully developed melt pool. I don't want to talk, I don't want to say the, this is actually, what is called, a fixed whirlpool. Is not actually fixed, because you will say steady state whirlpool, and you see some undulation and oscillation of keyhole is key for defect formation, especially for porosity. And it's happened that this research suggests it's happened at the melting front, actually. And the incomplete collapse of keyhole is observed experimentally as well, using the X-ray thermography here. And this is the same condition that we use for titanium 6-4. And this is a modeling and experiment has been captured quite well. If you can capture the full, I mean the collapse, the what is that, incomplete collapse keyhole at the bead of the plate or of the material here. How well can we predict the melting front boundary? This is another question, because I mean, for this specific application, the melting front boundary is just about, if I remember correctly, this is actually 100 micron, and you talk about 1 millimeter or more than one, I think it's 5 millimeter thickness. So the length scale are so different. So how can we capture this dynamic? This is another question to ask. Again, it's open for research. Compare with general feature with the melting front here in available thermography. We compare with the existing result in 2012 here, and then because that time we carry out the work around 2013-14, and this predicted melt front boundary is about 100 to 150, yeah. But it's actually good agreement with what we do in the experiment here. And extra information that I want to emphasize the melt pool dynamics. Is actually the we call fully developed shape. Is not steady state. I'm not saying steady state, because we believe it's not steady state. But doing the 2 kilowatt laser here, which is a lot more than weld additive manufacturing now. But I understand now we're talking about 1 kilowatt laser for AM, or a little bit more, 1.5. But this is for fusion welding actually, so it's quite high laser power, and you have different beam radius as well, as I said, and this is the detailed dynamic around the keyhole, what happened, and then sometime you may get some melt jet here coming out from the melt pool. And this we can try to understand and predict the porosity, and we hypothesize that the porosity might come from the according to the modeling suggests a causal mechanism of the keyhole partial collapse, which is actually something has been proposed long time without any supporting evidence. But we have demonstrated that using the simulation that, okay, if we capture carefully some moment, you will be able to trap or get some this kind. This is model, actually outline from the model. You can trap. Get the residual voice which is left behind after this fusion melting here, and then on the top surface you will see the track like this with some hole behind. I think this is something quite inspiring, because we seen the same as well on in the experiment. Okay. And we use some experiment to validate using the X-ray tomography actually to demonstrate the pore formation. The pore actually form in the quite perfect spherical form. But I mean, having said that, not every pore here is surface spherical, because titanium, we cannot map across. I mean, using XCT, micro CT, we cannot map every single pore here. As you know, limited by resources that time, but now you can see more if you use neutron tomography, you may be able to review all the porosity content inside, but resolution is another problem. If you get to see larger view, you may compromise resolution, but this one we take care of only one single pore or just few pore, and then we compare this morphology with what we predict from modeling. And this is the model we use to predict. And what is the important of this one is actually we try to estimate the location site of the porosity, which can be predicted by the CFD. So its location probably not quite similar, but again, we can capture what happened, and this is really the modeling. And then you can see that we also have the X-ray radiography as well to understand what is happening along the fusion path here. So we can estimate approximately the location site of porosity using CFD, and the pore distribution for the given process condition is captured while we use the X-ray thermography, and the pore is likely to form at the toe of the well of the bead, because the likelihood of the vortex flow, as I will show you earlier. Then radiography here shows the distribution along the fusion line. And next step, what we do is actually we do some parametric study to simulate this CFD framework. So parameter we use is a plate thickness, well speed, and laser power. Again, this may apply to additive easily. So we use the envelope of the process parameter here considered for the design space in the large pore porosity. So you will see this is I would say prediction plus experiment. You will see something we call processing map. So we map across laser power, well speed, and thickness. But if you are a metallurgy in the phase transition people, you may think this is a tertiary diagram. No, it's just a representation of the result that we have. So we can identify the red zone. Red zone means pore is big, and also we should avoid. We should go to the blue zone or black zone here, ideally, but you're not gonna get zero pore. If it's not if it's possible, I don't know if it's possible, but anyway, you can avoid the condition at the very intermediate laser power, but also kind of well speed is very low. If your well speed is quite low with the immediate laser power, you may be able to subject to the porosity area. And this is the sweet spot that we identify from the small DOE design of experiment we have, and also modeling to minimize the porosity here. So we get some sweet spot. And at this region, we have this one, so it's highlight as concerned. So we should avoid this. So this is something quite time and energy intensive that we come to this point, but this point will be useful for the next step for the microstructure prediction. So as I said, this is a condition investigated. If you think about additive manufacturing, the 1,000 watt or 2,000 watt is probably possible now for the new AM machine, which you may be able to have, but people not prefer to go to the full penetration mode because of the reason I just explained. It may be some instability in keyhole and trap the porosity behind the bead or in the structure, which is not preferable. What we're trying to do is try to understand how can we go just before the full penetration, but we heat enough of the material beneath the surface in order to get, but in this case, we try to present the extreme boundary, lower bound and upper bound. For example, what the microstructure happening at the conduction and full penetration. And then you will see, we try to predict the fusion zone basically based on the experiment and the modeling here using the micrograph here. And then we want to extend these, export temperature history to predict microstructure, and the thermodynamics boundary condition to represent the heat source, moving heat source especially. Not just heat source, it's moving. One of the things of heat source model, there is some more detail if you like to understand. We map only on the surface. So it's a volumetric heat, but we map only the heat on the moving surface. So you will see some thing look like absorptivity that people measure experimentally. So this is what we do. So I think this is much more detailed now, this presentation, not just showing the result. We used the Visual Basics in Excel that time to export or map the temperature field. Again, that time it's actually 30 gigabytes of data has been picked up. It's just a single bit of the melt pool, let's imagine. And then we use Python to actually generate input deck for the model that we use. And in that case, we co-develop with the commercial package here, Procast. I mean, I'm now moving away for commercial packages using open source code. And then using the VBA to scan data and then pre-process the automation. It's about 10,000. I think it's more than that at some condition. It's about 2,000 boundary condition at the melt pool surface here. And you use Procast to manually, at that time it's no automation, but we need to automate this one by Python scripting. But anyway, we pre-process this melt pool boundary here, and then we execute the model for the grain growth prediction. And this is, at that time, is an interface that we see. So this is what happened. You can predict what happened of the grain growth solidification, and then you see the moving liquid-solid interface. And this is a grain which is grow. A good question from the previous audience. They're asking about nucleation condition. We assume a normal distribution at the melt pool boundary at this time. But because it's valid assumption, because the parent material actually has the quite uniform, it's a rolled microstructure, so it's quite uniform after homogenization. So average grain size is kind of known for high standard aerospace application. So it's kind of valid assumption to make. I believe it's a 30 micron grain size at the roll or parent material. So we integrate this challenge by transfer across the length scale. So I hope you appreciate how complexity of the model, and in order to make it automate, it requires a lot of work, not just a material scientist. I appreciate my colleague who do a lot of programming things that make this work happen. And then we propose a proof of concept approach that we can allow user to access and manipulate the data. Important information that I want to say is that this temperature field is transient temperature, it's not static. So this required to represent the moving liquid-solid interface. That actually poses another challenge in the solid mechanics calculation later, which I will show you. So now we map the grain size. This all predicted. So this is the predicted grain size from the condition that I proposed to you. So this is a PV. So P power and V velocity. So we see you can again the same. You get the hot spot, and you get sweet spot for this processing. So in terms of microstructure. So to generate the process map here, a number of grain also important, because whether or not you represent the real fusion zone that we are looking at. And then this around the targeted design space to achieve required microstructure. Because some microstructure is very equax, some microstructure is very columnar grain, and they actually pose different property, which I will show you now. So in terms of microstructure, additional to what I show you, just the grain size, but from the coding skill, we can try to actually extract some information like the shape of the grain, 3D grain. We can calculate the volume, and then we can calculate the shape factor, which means we can surely quantify, surely quantify what is the grain. It's not just looking at it in 2D, but we are now looking at it in 3D and see the morphology in 3D, and then we calculate the shape factor, which means if it's smaller, it will be going to closer to circular. If it's larger, it's elongated, something like that. That's what it means. Or another way around, I'm sorry. Circularity is 1, sorry. Yeah, that means it's actually intermediate here. Sorry, my bad. Yeah. And then the shape factor we construct, yeah, if you see here, equax are closer to circularity 1, if shape factor closer to 1. If closer to 0, it's more elongated. But you will have the shape, which is in mathematics. You don't have only circular and elongated. You have somewhere in between as well. But most of the time, you get the grain somewhere in between. Again, this kind of information, I think, is quite difficult without any now. But there is a technique called correlative microscopy that you can serial section faster than before. And then you reconstruct 3D to see the morphology of the grain. But this is what we did from modeling long time back, I would say. And in addition to that, we also can predict texture as well. Textures. I think I may think you understand texture is orientation based. I mean, compare with the growth orientation of the material investigated. So in this case, we predict beta grain. Beta is the body center cubic crystal. So I'm sorry, it is too material now. Yeah, and body center cubic, the preferential growth, which is a minimum energy that material can grow in this direction, is 0, 0, 1. So that means if something misoriented from this 0, 0, 1 direction, this is mapped on this figure here. So this is predicted. So predicted texture also we introduced in the fusion process. I mean, quite early as well. So this is something we can get from microstructure prediction, and then you will see that from the conduction to full penetration or keyhole mode here, the well microstructure are different. And I will talk to you more. The different here will contribute to the different in the property. And equax grain microstructure can seen as a partial penetration as expected. So, but full penetration is more likely to be columnar grain structure. So again, this is what we try to compare. So temperature field now microstructure you see is more equax, and this is predicted as well. So we haven't had any EBSD data. Just want to let you know this is the beta grain structure. So, but what you see in the experiment after in postmortem, it will be alpha phase, which is because it's transformed from beta to alpha, and this is the last phase, which is similar to martensite in steel. And that means you need to do another programming to reconstruct back or work out from crystallography what happened if prior to this structure you need to transform back to beta. But anyway, that is a detail. So what we do, we link the code. So I show you in practice what we are doing, not just talking about that. So grain orientation has map on this space. So we have to communicate with Abacus, which is one of the greatest mechanical software that we use here. And then you will see it's not trivial. We need to map all information and then try to find a proper match to represent the microstructure we have. So we try to vary the mesh density, vary the mesh size from TED to HEC as well, and see what happened and how can we apply the algorithm to smooth the boundary. Again, there's so many challenges in translating model to another model, and this is something we try so hard to make this happen. And this is the concept. So we do the same from like experiment, but we do computational experiment as well. So we're stacking the 2D section and generate a 3D mesh here, Dream 3D. And we now try to run Abacus based on this simulated structure. And then this is we use in-house source code here to simulate. This is basically this is the result. So you will see that we try to replicate what happened in the as printed condition or as fabricated condition in this case. Another thing is actually now it's more about mechanical engineer. That you may need to impose some solid mechanics. But this solid mechanics is not purely solid mechanics. It's just, I mean, what you see here is just constitutive law that we trying to impose into the crystal plasticity framework that we have. You know, in 1 grain that we simulate, it should be contained is about 2 structure when we see it at room temperature. So this will be lab phase here, which is alpha, in the beta grain envelope. So, but this one, if you zoom in the inside, you will see there's some dislocation and the active slip system that actually promote or making the plasticity in this material. So this is, again, this is a solid mechanics framework by Hector Basotto and his colleagues here. So we apply this rule. This is a shear rate. I think you're very familiar with that. Dislocation density and then the shear stress thing. Yeah. So what you see here is a continuum dislocation dynamics framework that we try to apply this in a grain system, in an active slip system, using these things. And yeah, I don't want to go much because it's not my area of expertise as well. So we try to work with another colleague in the continuum mechanics people, try to translate this information across to another length scale, which is crystal plasticity for Titanium-64. And now this is actually come to the point that I want to show you, I mean, multi-scale things from beginning until the property prediction. And this is a good example that we can show you from the global, because before we do that, we need to run another model as well based on the CFD result we have. We need to run another global FE model. I mean, we have the local model from the what I showed you previously. We need to translate across somehow to the global model to predict the pre-mechanical behavior, what happened. Because in reality, your part is big, right? You need to predict something happen locally. What is a mechanical representation for that microstructure? Because we are talking, again, that is another challenge. How can we know the mechanical or initial condition for this your mechanical model? And if you like, this is the microstructure information that we created. We select some part here, apply some thermal boundary condition and also mechanical condition based on the global model here. And we try to predict the, we calibrate first for the beta phase at the 925 to 1000 centigrade using some experimental work that they have. Again, this experiment is actually forged material, but that is only the experiment we have at that time to validate the model. And then we try to apply this. Once we get some confidence, we apply this to the crystal plasticity model to predict the mechanical behavior. So this is another linkage. So we link later from lower length scale using representative volume element in FE to component level. Definitely we use Python scripting, abacus cube here, and then grain structure. We also fragment a pre-match FE model to CA to inform grain element set, and then we transfer this RVE, representative volume element, to finite element calculation. And output to the macro scale, constitutive equation of the two-phase material has been used. So this is the 9 condition that we have, and then we have 9 microstructure information here as well. So at different process condition PV in this case. So what we do is actually plasticity formulation we dictate by dislocation density, I mean an interaction, and the grain orientation is significant impact on the plastic response to the external traction. And then we use this set interrogate data from CA to feed into crystal plasticity code. I mean, just to summarize here, information here, apart from shape, apart from orientation and the grain size here, had been fed into the crystal plastic framework and try to predict the property accordingly. I mean, this breed again at different strain rate, actually. Yeah, you will see this is the prediction. And the property prediction has been predicted based on the detailed microstructure of the two-phase in titanium alloy Ti 64. I mean, during this fusion melting process, we assume that beta titanium would be dominant. Yeah, because that is some we call as solidified structure. We don't consider after they're transformed to alpha. We just concerned about assume this is assumption made. That means we propose that the deformation dominant from the as solidified structure. So beta grain is considered here. The yield stress derived from this microstructure shows some softening effect. That means this is in the, if you think about in the bead, in additive or whatsoever, this will be the sensitive zone because it's softer than other zone, right? And that larger density of grain can be modeled in the future. Again, the next question is how can we scale up? Again, this is the big question. And probably it's worth a 10 million pounds project, actually, this answer, because there's some project going on in US as well, for example, exascale simulation for additive manufacturing. Again, this is just a very first proof of concept modeling framework we have. So we reconstruct this Ceratomata microstructure with Abacus RVE using the UMAT, which is user material defined subroutine, apply the external traction to generate plasticity in a simple cube component. So we have microstructure really, and then we apply the boundary condition to simulate based on the global model that I said earlier. With the representative boundary condition, we can actually get some different in the full penetration and also what's that? And the partial penetration or conduction and keyhole mode structure. You will have different behavior from A to B. For example, in this one is softening, this one, another one is hardening. And that is something that we need further research to do more and more cases. I said to some of your colleagues, there's some group in USA just focusing on this work, but not actually used from CFD. They use from EBSD data and then try to actually rapidly calculate this one more and more and more. Example, Professor Koch from Johns Hopkins, I think, if I understand correctly. He is famous in doing this. I'm not, but just want to show you this is the direction that we want to integrate the information. And then, yeah, from the implement of this framework at a submodel level, because as I said, this is just a volume of one in the big model, right? So this is a representative volume that we use, and how can we respond it back into the bigger model is another question to ask, but not here to address, I'm afraid. So we believe based on the information we have, we may select proper constitutive behavior for the material that you use. That's why I said important of microstructure is variable. So we will looking at different stress component as well, strain, plastic strain at different component as a function of microstructure here, and feed into the global model. And again, this linkage is not really there yet, but this is just a proof of concept for a condition investigated here. And just want to summarize the first part, which is taking me quite long. So we can say that the framework here, I would say fusion process is applied for additive as well, as you know, fusion well process. But the CFD successfully showed the capability to predict the well-induced porosity, and this validated again the X-ray imaging technique. And this integrated to the Ceratomata grain prediction model. We do a lot of data processing to generate the microstructure, to represent the real microstructure from simulation. And this has been integrated to the finite element calculation using representative volume element approach. And this one can predict the component in the submodel analysis. And we believe this development of the crystal plasticity as a mechanical engineer, I think I need to corroborate with you, is actually going on. And what people said, want to do the, how to say, integration of the model and also machine learning. We may need to have a successful linkage of one model first and then try to approximate based on this understanding to future final element RVE model. And the process map that I show you, this is something us as an engineer want to have it based on crack criteria, based on whatsoever. For me, probably based on porosity, because we believe it's going to be based on microstructure prediction. This is something that model can do, probably rapidly generated the data than experiment and less expensive. Thinking about Thai 6-4 material, quite expensive material, you're not going to produce thousands of conditions to have the map. But hopefully we can have the model with, probably in the future we may use quantum computing to accelerate the calculation somehow. I don't know. Yeah, and then this multi-scale approach here has been developed to model this fusion-based process under CMV framework, and then CFD provide understanding of interaction of heat source and the material, provoking the keyhole dynamic porosity formation and whirlpool geometry to has been rationalized, validated, and predicted. Dynamic temperature boundary and shape of this has been linked to model the solidification in the conduction and keyhole mode, if you like, and then it shows that equax grain actually form in the conduction mode and the corona grain mostly found in the keyhole mode. Again, this one is carefully observed in the condition we know very well. So this new creation condition, I think, is varied to assume, but for additive, it's so dynamic, so kinetic. So we need further study to confirm what is the real condition that represent the process. I believe it varies from material to material, condition to condition as well. And the grain morphology reconstructed for crystal plasticity calculation using this new two-phase titanium alloy constitutive law. Again, if you change to nickel, things may change. If you change to steel, things change again. I think you appreciate that. And the steel, you may change a lot because steel is so powerful material on Earth that you have so many variety of microstructure which actually contribute to different behavior, a lot behavior. So use stress prediction, which is static. We're not predicting fatigue yet, which is the things we want, because if it's rotating part, fatigue may be important property, but it takes a lot of time and effort to make that. We will cooperate with other groups around the world. So this is the first part that I believe this can translate to other things. For example, like rotary friction or linear friction that I mentioned earlier. Okay, I was thinking there is another part. I'm sorry, let me. So, yes, I think probably it's good time for discussion. I think it's actually I speak too fast, I would say. Do you have any question? This time, I think I don't take any question during the, yes, please. Say again? Good question. The answer is no. This is a simple solidification model. Yeah, because let's imagine we're talking about few thousand, and that time is actually 2013. It's just a proof of concept that we integrate everything. As people said integration, but no real example. And we try to create the first real example that we integrate everything. And this is what the thing. So at that time, we co-developed with the commercial software packages to apply this. So we need to use simple kind of just follow the thermal gradient direction to grow the grain. Yeah. But complexity can be added, but if you have a lot of computational resource, I think that's fine. it's okay, but yeah, it's not just easy and simple. But we can do that now. But let's imagine we're talking about not only 9 microstructure here. We're talking about, actually we simulate more than this, but we just show you the 9 microstructure here. So thinking or considering that factor with the computational resources we have, if we are a national lab, probably yes, we can generate tons of data without any concern. But we need to compromise with the resources we have as well. It is just a proof of concept. So the model we use is not what I present you last lecture. No, it's just simplified version. But we hope we can simplify something based on more complicated simulation that we have and take some important information to get this microstructure. That is the aim, because we cannot simulate everything in very physics-based simulation all the time. It's impossible in a component scale analysis anyway, right? But people talking about what is the important parameter, important information. That is the key for this kind of model to tell, I believe, yeah. Is that okay? But if you fancy, if you are a metallurgist, you may want to do very detailed segregation profile. It's okay, but it's not in this length scale simulation. It's another length scale of simulation. You may need to do surrogate model for that and then export, global, local again, find a numerical way to do that. Yeah. Oh, that is assumption made. This structure assume is a plier beta grain. So we assume that the deformation taking place during beta transformation. So because after about 950 or 850 to 950, based on the different grade of pi 64, the beta will transform to alpha, right? And then we assume that deformation taking place just before that. Assumption made. Yeah. in this case. But again, the detail. Then I think I will show you example. I think probably it's not, if not tomorrow, the day after tomorrow, that we use direct energy deposition, apply detailed microstructure. Apart from solid liquid gas transition, transformation, we apply solid transformation as well. You will see that it will change the microstructure from beta to alpha. And that is the detail I'm going to show you next lecture. But for these cases, no. Assume that things happen before that. But I appreciate you yourself. But constitutive equation may be able to capture what you said. But the complexity had to come to constitutive law. That means you need to say that this is a pi beta grain. During deformation with the cooling, you need to impose some crystallographic orientation that involves some transformation, and then you introduce some deformation due to that transformation. So complicated. Yeah. Again, this one is, I would say, is a representative result that we show you. It's probably a bit overestimate, because beta and alpha, some of them actually, because we assume that we simulate the beta phase. Is that okay? And then with beta, if you change BCC, is BCC beta. And then if you change from equax to columnar, based on the constitutive law we have, it behaves like this. Again, this is just the simplest plasticity model we apply. Detailed calculation needed. We just, this is a proof of concept framework that we propose. Yeah. So I appreciate that, but I think that suggests that detailed research needed for, for us to work on. And then we need some mechanical engineer to help us. I'm not mechanical person, I'm material people. Yeah. Yeah, I'm. We plan to do, but not yet. But I would. This is good question. The answer is not yet, because if you impose that porosity, you may need to impose another complexity on the fracture mechanics, which is not yet done. I'm not. I need to cooperate with some other people, maybe you. But not yet. We haven't done yet. But in principle, yet we can generate that. We can select the zone with porosity, which we have, but I haven't shown you here yet, because I think we have faced some numerical challenge around that feature. Yeah. Depends. I think it's heavily depend on the material system you investigated, depend on the condition you investigate. I think, again, I think I don't know the answer, which one is better. But for my condition, let's say in titanium alloy, I think this is probably the best way we need to take, but it's still challenged as numerically and also resources needed. Numerical challenge is one thing, require a lot of resources. But you said you asking the right question actually. But in order to answer your question, we may need to try both way and see whether we get the same result, or the result that we obtain from both way is actually the same from experiment we observe. Again, modeling is just need to work with experimentalists to make sure that this is the model have predictive capability. I think it's a subject of future research. Yeah, global boundary condition will impose you the initial mechanical field, because we don't know what is the initial mechanical field for this situation. In this situation, it's just, let's say if you want to repair using fusion welding, for example, you need to cramp the both end of the part that you're going to build, right? And then you pass the laser through. And we want to know the initial mechanical field that happened to this structure, what happened, and then we want to see how this mechanical field evolved with the structure given here. So that's why we need, that is another complexity that I think in the solid mechanics people know, that what is a representative, physically representative of the boundary condition that gives a meaningful result to you. Yeah, that's this reason why we need to do that global model. I think you have who other, yes please, yeah.
My question is regarding the previous lecture on the microstructure model.
Okay.
Your model was developed on cellular FMRF, but there are other models like LVM, that is original method. So I want to just, based upon your experience, which method is more suitable for accurate prediction of microstructure? Because I am just a beginner in this microstructure.
Yeah.
I have gone through literature that I found researchers are using most of the models to develop a safe model to microstructure.
Yeah.
So which is suitable and more accurate to microstructure?
Yes. This is very good question actually. And microstructure modeling in additive manufacturing is become more and more popular. Previously, I would say for the simplicity, I think the statistical approach like Monte Carlo or the Lattice-Boltzmann kind of things, it's just simple, it's too simple, I would say. There's no physical meaning there. If not, you have to create a new framework based on that numerical framework to impose some physics. But I find it actually, I want to highlight your question. You say accurate prediction. Again, what does it mean by accurate prediction? That means you need to correlate with experiment. But if so, we can impose more term, let's say in phase field or seratomata, that addition to the equation easier, and then we can. That is my preference. It may be wrong from some other people. They may say Lattice-Boltzmann is better, but for me, my preference is phase field or seratomata, because, for example, if this microstructure in additive, especially now, you have the other process you may know, it's called field-assisted additive manufacturing. So if you want to impose that as a function of magnetic field, electric field, or whatsoever, you can do it with physical term, physics-based, tools. But for that statistical approach, I'm afraid it's so, it's not something I prefer, So I believe this may be more accurate than other approach, When you can incorporate all physics-based equation or principle into your microstructure is more preferable, Yes.
When you are discussing about a multi-scale model,
Yes.
as we all know that to have a very tiny melt pool, we need to have something like laser spot diameter of 80 micron or something.
Mm-hmm.
But you go something like atomic modeling where you have shown a picture of molecular dynamics. That's a representative. So how feasible is that even though the melt pool size is around 100 or 200 micron, but how that larger scale can be converted into atomic modeling to simulate the process? That's how.
Again, we need to be careful about this. So we need to ask the right question. So what is the use of the atomistic simulation? I would say to you a few examples. Like atomistic simulation is not going to simulate in a melt pool size. Do you agree with me? Yeah. And what we need from atomistic simulation is actually some property that we cannot measure. For example, the vapor property. For example, some interfacial energy of something, I don't know, that kind of property we want to link from lower length scale to meso length scale. So that is the use of the first principle or atomistic calculation, actually.
Actually, my question was only that whether we can simulate that process modeling on atomistic, or we
No.
use that.
If you have quantum computer, probably yes. So you may know that there is some paper from China, I think probably Tsinghua University, on the wetting process. They use one bead of the doublet using atomistic calculation. Yes, it's possible, but I think your domain will be limited by the computational resources. But again, I don't know what is the use for that if you don't have the target property, or because basically it is electronic property that you get from atomistic calculation, right? That people want to do, or the some thermophysical property. If it's the case, probably yes. But if you just want to simulate melt pool, I don't think so. It's not the right tools for that, I think. Yeah.
So my question is regarding cladding.
Yes.
You have mentioned that on last class, like as printed model you are selected, or are you done any surface treatment? Because what is the role of surface roughness over there in the cladding?
Very good question. We have simulated something on the surface roughness. There is some impact on that, but I think it's probably better, I think the detail of that will be discussed tomorrow in the lab session. So we dedicate 3 hours for that. And another reason, because I'm not actually, conduct this work myself, is my postdoc. So it's better to ask him, and I can help tomorrow. Yeah. Yes. Are there any other questions? Yes, please. Yes.
For all the CFD simulations for single tracks,
Yes.
multi-layer, what are the thermophysical properties? Means you use all the properties at room temperature, or do you go for high temperature?
No. We use a temperature-dependent property available in various forms. This is a good question. This is something I suggest to my research council in UK as well. So the data that we use to represent this case is actually based on the data that we use for casting forging, which is not optimized for additive manufacturing. As you may know, the powder and the bulk property are different, right, from mechanical model or mechanical engineer perspective. So we need some way somehow to treat this property based on whether you use the term like 1 minus porosity of fraction to lower the stiffness, for example. But you may need some way to treat this property. But we don't have a kind of good data set for powder property at all. I know some company has done that, and they may sell you quite highly costly. Yeah, I think I know some company, for example, a thermodynamic company like Thermomechanical. They developed the non-equilibrium, the database for AM, and that means the database there is so valuable. Again, you are asking the right question. Still, I'm not saying problem, but I would say the area for improvement. And this can be calculated or done by probably atomistic calculation. I'm not sure, because atomistic calculation, they're not very stable at high temperature as well, only 0 Kelvin, right? For the sake of finite first principle calculation, they also has some assumption. So how can we represent that? But they still have some elevated temperature first principle calculation, which is more effort and resources required for doing that. Again, you're asking 10 million project question again. Say again, I'm not getting.
So suppose if you were referring to the non-equilibrium temperature-dependent properties of the material, okay, like TI64, ALSI. It's not non-equilibrium. We said temperature-dependent property.
Okay, so due to the non-equilibrium nature of the components, means precipitation and all those things, there could be some effect to the temperature-dependent property as well. So those effects will be more prominent below solidus temperature.
You asked a very good question, but the thing is, that is assumption. We say that this intrinsic property we use, thermophysical property, doesn't change. That is the assumption made doing this, the rapid heating cooling, because we believe that's the intrinsic property. Again, you may see otherwise if you have very detailed characterization and prove that it's not. Again, we're still waiting for experiment to inform us what is the things. Yeah, that's very good. But I mean, if you see a rapid fabrication community, they use probably for different material system. They're probably looking at metallic glass, something like that, right? So it's again different application for, it's not structural material, I believe. But I mean, we may need to. I mean, that's good. We can generate some idea for research on that with some people in the field. But for me, I don't know yet. If experiments suggest that, I think we need to find a way to simulate that. That's what I can say. But at the moment, the assumption we believe, we assume is that the the property is intrinsic to the material. Whether or not it's imposed, whether or not the effect of the non-equilibrium rapid heating will affect that, we don't know yet, actually. Yeah.
Thank you, sir.
Any other question? I think rather than question, you may feedback what we have had to say. Lecture for in the last. I mean, this is the fourth one now. Probably it's halfway through my lectures part. I mean, definitely. I mean, 2 sessions tomorrow. I will deliver first session, and the second 2 sessions after that will be together with my postdoc Joy online. I mean, so far, what do you think about the lecture? Is that good, useful, or something you want to add me to add more, or you think I should leave more time for question? What is the thing? Because otherwise, I will occupy all the time for the lecture. Yeah. Are there any suggestion, comment? Sure. Okay, I will rearrange accordingly then. So something like this is better, right? Rather than talk. And actually, I also don't know who here are PhD scholar or PhD student here. Wow. Okay. So your research here is based in IT, Oracle, or somewhere else as well? Say again? Other institution, okay, sure. Say again?
Like validation. We
Yeah.
ask about validation because of always percentage of error, how much we always approximation what we are getting. So how do we validate whatever the result now stress strain curve, whether it's isotropic or anisotropic, orthotropic, which type of properties you consider to get that simulations?
Yes, you are also asking the right point question. So actually, we base on the data currently available for us. So you are right, the one we use to calibrate the model is a forged material. So it's not actually the right processing route that we use. But again, this is I'm not saying problem, but this is an opportunity for research to do more like industry to generate data. Because as you know, forging or casting is a long-standing metallurgical process. So they have a lot of data generated. So we cannot ever generate those probably worth several million pounds of data, right? So we need to borrow that. You asked the right question, actually. So the suggestion or advice to the company is that I think now they are doing that, to generate their own data based on the material they have. Because even you're talking about the grade of steel, but you still have different grade for different company, for example. And that will be valuable data for you. But how to use it, that is the question. Because when you have the data, you may use for machine learning, you may use for CFD, you may use for blah, blah, blah. But I think to use that is the question. Whether or not this will change significantly from the database we have, or you may find something completely different saying that this process alter the thermophysical property. Again, I don't know, this is fundamental question which I cannot have the answer now. I also don't know the answer as well. So we don't know, but this is an opportunity for research, actually. Or probably first principle calculation can tell us. I don't know.
For isotropic, but when it comes to
Yeah, anisotropic, yeah. Yeah, I mean, something in the micro mesoscale level, we all know that what happened, but you're asking about intrinsic property, right, of the different material with different processing. I think you may appreciate with me that if you do casting, I think you may see some paper talking about this is a casted material, this is a forged, this is a welded, this is a wrought material, hot working. They're all different property. And that's why I said this is an opportunity, I would say. I don't say this is a problem. This is an opportunity for us to collect it or make it even better. Again, it requires a lot of experiment. Again, what I said here, you need to inform me, oh, Shinapat, this is not right. We need to calibrate with this set of data instead. And then that is the way to go forward for modeling to predict out of range property that you may not have, or because we need to identify that as well. I would say this is a kind of working framework, just show proof of concept what we have. Yeah. Is that okay? I think that is the key, right? Otherwise, there is no single project funded at all, because if I do everything already, I think there's a lot of things to be done. Yeah. Okay, I think it's time, Professor Kumar. What should we do? Or?
Yeah. Thank you for your nice lecture.
Thank you very much. Yeah.
Yeah, and then now, now we'll break for the lunch, and we'll come back at 2 o'clock. Yeah.
It will be lab, right?
Yeah, it's
Labs, not me. I think it's your.
so it's 2 o'clock here at the same place.